In this problem, a stone is dropped from the roof of a 30-meter high building, while a second stone is thrown upward from the ground with a velocity of 20 meters. The question asks, when will the two stones be at the same height, and what height above the ground will they meet? Let's start with our picture. Here's our building. Here's the first stone. I'll just put a 1 with it. It starts at the top, and it's going to fall towards the bottom. And at the ground level is our second stone, stone 2, and it's thrown up with a velocity v2 equals 20 meters per second. We can assume the velocity of ball stone 1 is at rest when it's dropped. It's not thrown vertically or thrown downward. Let's also make sure we specify that up is our positive direction. And when we're talking about position, both of these objects are moving along the same vertical line. And so we can describe those positions with the lowest point. We'll call this position for ball number 2. We'll call it its initial position of 2 at 0 meters. And we'll call the initial position of ball number 1 up here at 30 meters. And so if I had a tape measure, I would have 0 meters here. I'd have 30 meters here, which again are positive direction moving up. Now these objects are going to meet somewhere in the middle. And what we don't know is what this final position will be and how long it will take to get there. What we do know, however, is that both objects will be at the same position. So the final position of ball 1 will equal the final position of ball 2. So we can call them both just x final. And the same thing with time. The time for stone 1 is going to be the same time as stone 2. If we started a stopwatch when the problem started, it would read the same thing. We can call that t. So they share a common variable. And when we see that, you should be thinking a system of equations. So I'm going to set up, and again, the other variable we haven't put in here is that you've got gravity, ag, which because up is positive, we'll call that negative 9.8 meters per second squared. We have two objects, and we can describe the motion and the position as it relates to time of each object with our position function. Our position function is x final equals 1/2 at squared plus v initial t plus x initial. Now again, we also have our v final equals at plus v initial, and that would describe the velocities of both balls at any given time. But in this problem, they only ask for the position, x, and they ask for the time at which they meet. If they wanted the velocities of the balls when they met, we could use that second equation. But since I have two stones, I'm going to set up my ATVX table for each stone. Stone 1 has A, T, V initial, V final, X initial, and X final. Here's my ATVX table for stone number 1. And for stone 2, I have an ATVX table. And if I want to, based on my picture, right, I can put a 1 subscript under all these and a 2 under all these just to be consistent with what my picture looks like. Again, these subscripts are just labels on these variables. They're both the same variables, but they're different for the objects. A is going to be negative 9 meters per second squared for each object. They're both on Earth, experiencing the gravitational field of Earth. We don't know the time for each, but we do know that T1 equals T2. V initial for the first stone, it starts at rest when it falls. Its final velocity, we actually don't know. Now, it's going to have some speed that it gains due to gravity, but we actually don't know what it's going to be at the position where it meets. It starts at a position of 30 meters, and it finishes, again, not at the ground. Eventually it'll get to the ground, but when we look at the F subscript for final, final really only means at the position of the object that we care about, which is going to be where they meet, not necessarily at the ground. So we don't know X final. And for ball 2, or stone 2, again, we don't know time. It does have an initial velocity, which is positive 20 meters per second. It has a final velocity when it gets back to the ground of -20, and at some point it'll be 0 at its peak, but we don't know necessarily where along its path it's going to intersect, so we can't assume anything about the final velocity. The initial position is going to be 0 meters, and again, that final position, x final 1 equals x final 2, because they're moving along the same position and they're going to meet. So once I have this, I can plug in those values into my position function for each one. So for the first object, x final equals 1/2 times -9.8 times t squared plus the initial velocity, which is 0 times t, plus its initial position. So that's ball 1 or stone 1. Stone 2 is going to have an equation. X final is 1/2 -9.8 t squared plus its initial velocity, 20t, plus 0. And if I simplify and clean it up, I'm going to get two equations again. X final equals -4.9, that's half of 9.8, t squared, plus 30. And the second stone is going to be x final equals -4.9, t squared, plus 20t. So I have two equations and two unknowns. We have a system of equations. And since we have two equations with the same two unknowns, we can solve for both of those unknowns. Now, because x is already isolated, what makes sense is to use substitution. So since x final in this equation equals -4.9 t squared plus 30, I can substitute in it for that x final. And it gives me a new equation, which is -4.9 t squared plus 30 equals -4.9 t squared plus 20t. And now we can solve that equation. It only has the variable t. And we have -4.9 t squared on both sides. We can add that to each side, or since it's on both sides, if you think of it like a scale, they can cancel. So we get 30 equals 20t. We can divide both sides by 20. And so t equals 30 divided by 20, which is going to be 1.5. So that's going to be our time that they're going to meet. So now that we know how long it's going to take, I can actually use that time to plug into either function. And so for part B, so this is my answer for A. And for part B, if I want to know where they meet, at what height, well, that's going to be the final position. X final equals, and I can use either one. So I'll just use the first one, -4.9 t squared plus 30. And I'm going to plug in the time that I evaluated, 1.5 squared plus 30. And when I plug that in my calculator, I get -4.9 times 1.5 squared plus 30. And I get a final position of 18.98. X final equals 18.98 meters. And that's the height above the ground that they're going to meet, which again should be between 0 and 30, which makes sense in our problem. There's our work. There you go.